Example 2.A.2. Given. The belt-driven pulley and attached disc are rotating about a shaft passing through O. At a certain instant, the speed v of the belt is known to be 1.5 meters per second, and the magnitude of the acceleration of point A on the disc is 75 meters per second squared. Assume that the belt does not slip on the disc. For this problem, find, at this instant, the angular acceleration of the pulley and disc, the acceleration vector of point B on the disc, and the acceleration of point C on the belt. First, we will begin by writing out our given values from the problem statement, and also write out what values we need to find at the top of our page. To begin with, we're going to write out the acceleration equation of point A with respect to point O. When writing out this equation, we realize there are a couple of variables that we don't fully know quite yet. So below our equation, we're going to write out every variable and what we know about it. We know AO is fixed, so therefore it would equal 0i plus 0j. Gamma we don't fully know yet, so we're going to solve for it above by taking v over r in the equation. We find gamma to equal negative 20. Now the only variable left is the position vector r a/o, which from a diagram we can find to be 0i minus 0.15j. Now we will take the values we just found from above and plug them back into the acceleration equation that we have from earlier. Now we know from our given values that the magnitude of the acceleration at point A is 75 meters per second squared. So if we use the values we have currently in the acceleration equation for the magnitude at point A, we can find what the angular acceleration of the pulley and disc is. We then find the angular acceleration of the pulley and disc to be 300 rads per second squared. Now we will use the acceleration equation of point B with respect to point O in order to solve for the acceleration at point B. Again, we will write out all the variables from the equation below and what we know about them. We now plug all these values back into the equation from above in order to solve for the acceleration vector at point B. We end up finding that the acceleration at point B is 20j plus 22.5i meters per second squared. Now, for the final step, we'll use the acceleration equation at point C with respect to point O in order to solve for the magnitude of the acceleration at point C. We find the acceleration at C to equal negative 22.5 I meters per second squared, or just negative 22.5 meters per second squared. And that concludes our example.